What's the usage model that requires this?
That sort of ties into the business model, but the obvious one is anywhere where you have large numbers of concurrent Java threads, which would be most people who are running web servers, app servers, kinds of things, big data center apps, where thread level parallelism is complicated.
So what would be your cost time target for that?
I don't know that we've defined a target. I think we'll be somewhere in the order of small counts of milliseconds. Certainly well under, half a second ever. I don't want to say an order of magnitude under half a second ever. So something not hard real time, but something good enough for interactive, display my data kind of things.
I'm expecting you won't be able to answer this, but I'll ask anyway. The hardware techniques you're using, do you see any reason why they couldn't be incorporated in standard processors? I mean, aside from patent issues and stuff, what I mean, technically, are they really designed for large-scale systems, or are they suitable for
Some of the stuff clearly can go into existing processors with sort of minimal hacks. I mean, well, I'll get to some of these things as I roll along. Yeah, a lot of these things are minor tweaks. You need to go, somebody who knows how to do the CPU layout, go hack the core. The Intel could go add these in the next generation x86 with another prefix on them, kind of things. And we have patents on a bunch of interesting things that we think are bottlenecks to somebody else building the kind of system we're building, but by no means on everything, and maybe some of these instructions will show up. So then we looked at heap allocation because it has this hard pattern for your caches. Basically, heap allocation is it's a streaming memory reference. It works its way through a very large pile of memory. Your young gen might be, well, for us it's gigabytes, but it might be many megabytes. And it's constantly wanting to read in new fresh memory, which you immediately initialize. And so you've just read something which is dead. And then as part of reading something in, you have to throw something out. And what you throw out is probably a young gen object that's been around long enough to live through your cache to get to where it's going to be thrown out, which means it's probably dead. So we've tried to optimize this. So basically, anytime you stream through memory, you have some fairly easy to optimize kind of pattern. And so we have, well, I'll go on here. We'll take a look-see. So the normal sequence for a heap allocation is some sort of test and bump. Yeah, this is me talking about streaming through memory. And usually when you work into the new generation, you're always getting cold cache misses to get data in. And, oh, here's this. I'm on one slide ahead of myself. So yeah, you end up paying a cold cache miss to load data in, but to get it in, you had to evict some object which was 95% chance dead. So we can do a little better. We can avoid the read fairly easily by doing something similar to zeroing in the cache instead of actually trying to read the data from memory and then filling it with zeros as soon as I get it into my cache. So I just avoid the memory read bandwidth issue altogether, and I can cover the latency to be cache coherent and all that by just prefetching it far enough in advance. So I fill a pipeline of zeros out ahead of me that's as deep as I think I'm average going to need, and when I make a new object, I suck up some number of cache lines, which are all pre-zeroed and hopefully coherent, and I go issue that many more prefetches far enough ahead to refill the pipeline for the next allocation.
So isn't everything you just described is about 10 years old in terms of what the hardware does that you buy off the shelf and so on?
So DCBZ has been around a while. Is that what you're asking?
No, I'm just talking about, the cache misses don't do fetch on write. I haven't said 1995 hardware and so on. I mean, this is good. This is exactly right, but I don't.
I've certainly seen plenty of caches. Let me read the other around.
It's totally not universally implemented.
It's not universally implemented that as soon as you write that first word of the header, you end up with a cache line that's got old data and new data in the same line. And so now you have to have the bits in the hardware that tell you that these words are invalid and these words have dirty data. and that's not universal by any means. So it is good for object allocation to have that pattern, but that's just not the common pattern out there. In addition, well, so you have a coherency issue still. So once you've made a line dirty in your cache, you can't, it has to actually sit in your store buffer while you try to get coherence. So you want to put a dirty line in your cache, take this word you just wrote, store it in your cache. Your cache is full, you have to evict something. Separate from that, you have to go tell all the other CPUs floating around that you own this line, they don't. So pipelining that is a win. It turned out to be, I had numbers on top of my head at some point. It was an interesting amount of data of not read cold cache miss data. It wasn't the cache miss that did, it was the bandwidth. There was an interesting amount of bandwidth reduction for playing this game.
So the power instruction, is that a privileged instruction or it's?
It's some interesting coherency rules with it, but I don't believe it's privileged.
No, it's not.
It plays games with if you have cacheable memory or non-cacheable memory, and there's some other games involved with how it interacts with other people's coherency view of the world. I don't know all the details. Okay, so stack-based allocation is a way to do better yet, and that's just to avoid having to write out the dead data that comes when you have to evict a line out of your cache. And typically doing stack-based allocation requires some sort of escape analysis, which is both, it's a compile time kind of thing, it's fairly expensive, and conservatively correct. So we have a write barrier that detects stack escapes. So it detects when I try and store a young frame pointer into an older frame or into the heap. And if it detects this, then I'm going to trap and fix up. Trap and fix up involves moving the object to the proper lifetime it's going to have, and a thread level GC to update the pointers on the youngest few frames of the thread that actually can have a pointer to it. And so fix up's moderately expensive, so it needs to be rare. It turns out that there's these two things you can do, and they both converge rapidly in practice. The first is that you tag allocation sites with a frame delta. If you come across an allocation site and his delta is 2, it means make the object 2 frames up. And if that object later escapes to a higher frame, you raise the delta on the generating site. Next time you come around to that site, it's 3 frames up, or 4 frames up, or whatever. And it rapidly converges in practice. Same for making your stack frames the right size. On entry, it's so big, and if you try to allocate a guy in there, it's a test and bump pointer, it overflows at some point. You make the frame bigger next time around. So the next time that method's called, you get a bigger frame, it doesn't overflow. These converge after a few thousand escapes during startup, and then that's it, they never blow out again. The rate of failure beyond the first minute is extremely small. So it ends up that we can do detection instead of analysis, and there's no upfront costs and compile time, and it works on interpreted code, it works on unoptimized code. It works when the analysis can't prove it to be correct, and it works even when the analysis has no chance of proving it, because there is a path where an object might escape, you've just never taken it, or maybe you take it so rarely that it's worth fixing it up on the occasional escape. So it turns out that we can get about half of all objects allocated on the stack with no compiler analysis whatsoever. So it's interesting.
Is this mostly a win because you have write barrier?
Yeah, the write barrier is cheap. We have it in hardware. You could do a write barrier in software which does the right thing,
right.
And whether or not it's cheap enough depends on how expensive it is for you to do the necessary set of compares and branches and tests versus the frequency of doing the write barrier. Versus, the reason to stack allocate is that you're saving some bandwidth. And if you're short on bandwidth, maybe it pays off in your big out of order box, you got enough resources to throw at it. There's interesting trade-offs.
So if you had a thread local nursery, wouldn't you have the same effect? I mean, if it was the right size, if it was size small enough?
we've tried keeping the youngest gen small enough to fit in your cache. And it's somehow, it's not as,
And not only that, he's saying you wouldn't need coherence in that cache.
well, we don't on these stack objects either.
Well, yeah,
That's actually, all right, so separate things. The stack doesn't need coherence, and we know that, and we can play games with locking on that. We have tried shrinking a nursery down to where it's small enough that if you do the collection, you would stay in your cache. And the overheads of doing the collection versus the rate at which the nursery runs out don't pay. It's always make it giant, giant, giant. You give enough time for all the objects to die, and the live set is itty bitty. Whereas if your nursery is the size of your L1 cache, things aren't dead yet.
So your stack, your frame location heuristic, does that get screwed by you got a function f that creates a linked list of some indefinite size that it and all of the pieces of it are dead 2 frames up. So that 2 frames up.
So I'm going to run out of time. I
Yeah.
have a separate talk that I was going to do here on stack-based allocation. And if we have a chance, I'll go in one of the BOF times. But right now, let me roll on.